Hello everyone, in this lecture I am going to discuss the measurements. So this subject is microwave and radar engineering. So in this topic I am going to discuss about the measurement of VSWR, measurement of insertion loss, measurement of attenuation, measurement of impedance, etc. So first of all I am going to discuss the measurement of low VSWR. Basically, VSWR is voltage standing wave ratio. In this voltage standing wave ratio can be considered in two parts, that is low VSWR and high VSWR. So if the VSWR value is less than 10, then we can say that this is the low VSWR, and if the VSWR value is greater than 10, then we can say this VSWR is high VSWR. So for measuring this low VSWR, this setup is shown in the slide. So in this setup you can see that basically there are 6 blocks. First one is microwave source, second is pad, third is slotted line, fourth one is crystal detector, and fifth one is DC millivolt meter, and sixth one is the slope. So in this setup you can see that by using this setup we can measure the VSWR. So in this in this setup we are using this slotted line and crystal detector. Slotted line is used for getting the maximum reading of the meter, that is DC voltmeter. DC millivolt meter is used here, or you can say this is the VSWR meter. So for by varying the slotted line or by moving this slotted line, we can get the maximum reading of the VSWR, and there the attenuator is used for adjusting or getting the adequate reading on the meters. And this attenuator is now adjusted to get the full scale reading in the meter, that is V maximum, and the probe on the slotted line is used to get the minimum reading on the VSWR meter or DC voltmeters. So by getting the maximum and minimum value of the DC by getting the maximum and minimum value of the voltage or the slotted line, or reading of the maximum or ratio of the maximum and minimum voltage, gives the value of VSWR. So in this way we can measure the VSWR if the value is less than 10. If I know this, the value will come less than 10. Then for measurement of high VSWR, we are taking the same setup. The only difference is that we are using the slotted probe is inserted to the minimum voltage, and by getting the after inserting the probe, we can move the probe to the distance. We can move the probe from distance d1 to d2, and at that point we can measure the maximum and minimum voltage of the source from the that we have given to the input. So in this way we can measure. From this figure it is clear that at distance d1 we are getting the minimum power point. At distance d1 and d2 we are getting the minimum power point. At V minimum we are getting the maximum power point. So at distance d1 and d2, that is double minimum method. And by using this method we can calculate the VSWR by using this d2 minus d1 is nothing but d. We know this, the guided wave wavelength is lambda g, and we can calculate the lambda g by using this lambda naught upon 1 minus lambda naught upon lambda c square. So how will I calculate this lambda naught? Lambda naught is nothing but the c by f, where c is the velocity of light and its value is 3 into 10 to the power 8 meter per second. So for T10 mode, lambda c will be equal to 2 alpha, and lambda naught is equal to c by f. So guided wavelength will be equal to the lambda c is equal to lambda naught upon 1 minus lambda naught upon lambda c whole square. So we can calculate this VSWR by using formula lambda g upon pi d2 minus d1. So d2 minus d1 is nothing but the distance between the two minimum power points. In this way we can measure the VSWR, high VSWR. Next is the impedance measurement. So for impedance measurement, basically there are three methods: using a magic T, using a slotted line, using a reflectometer. So impedance measurement at microwave frequencies is accomplished by measuring the reflection coefficient caused by the unknown impedance when it is connected to the end of the transmission line of known characteristic impedance. So the impedance is a complex quantity, that is we can represent this R plus JXL or JXC. So both amplitude and phase of the signal we have to measure. So impedance at microwave frequencies can be measured by any of the following method that has been that is magic T, slotted line, and reflectometer. So using a magic T, we can this magic T can be used in the form of a bridge for this measurement. So in this four arms, this is the setup basically. So in this four arms of the magic T, a standard variable impedance is connected in first arm, and the unknown impedance is connected to the second arm. So, and a microwave source in the third arm, and the null detector is connected to the fourth arm. So what we are doing, we are connecting a standard variable impedance to the first arm, unknown impedance to the second arm, and microwave source to the third arm, and null detector is connected to the fourth arm. So this is the figure of the magic T. So it is clear that at port 1 we have connected the standard variable known impedance. At port 2 I have connected the unknown impedance. At port 3 I have connected the microwave source, and at port 4 I have connected this null detector. So by the property of the magic T, microwave power from the source is divided equally between the arms 1 and 2. These impedances are not equal to the characteristic impedance, so there will be the reflections from arm 1 and 2. The reflected power enters at the port 4, which is connected to the null detector. So port 1 and port 2, the microwave power is divided equally between the port 1 and port 2, but in the port 4 is connected to the port 3, that is null detector. Port 4 is connected to the port 3, and when the bridge is perfectly balanced, there is 0 in the null detector. So what is the role of this null detector? Null detector is used for detecting the unbalanced value. So when the bridge is perfectly balanced, then there is a null detector will give the 0 value. If the bridge is not balanced, then it will give some value. The standard variable impedance is adjusted till the bridge is balanced. So we have to vary the standard variable impedance, that is at port 1. And this situation corresponds to both the impedances being equal. So we can in this way we can measure the unknown impedance value by using the standard variable impedance value. Next method is using slotted line. So this is the simplest method for measuring the unknown impedance. The unknown impedance is connected at the end of the slotted line, and the microwave power is fed to the setup. In this the unknown impedance reflects a portion of this power, and there will be standing waves. The reflection coefficient is measured by probing the standing wave fields in the slotted line. The reflection coefficient is given by ZL minus Z0 upon ZL plus Z0, where ZL is the unknown impedance and Z0 is the characteristic impedance, or you can say ZL is the load impedance. If rho is measured and Z0 is known, then ZL can be calculated. This is a simple formula. Since the impedance is ZL is complex, so both the magnitude rho L and phase phi L will be equal to rho L is equal to rho L e power j phi L. So magnitude of rho may be found from this value of rho. Rho is nothing but VSWR minus 1 upon VSWR plus. So we can calculate this. Calculate the value of rho by using this ZL and Z0. And if the VSWR is known to us, then we can calculate the value of rho also. So this is the setup for the for load impedance measurement. So in this tunable probe detector is used and the slaughter line is used. So first the load VSWR is measured to find the magnitude. Then the distance between two successive minima is measured to determine the beta. Beta is nothing but the phase constant. Beta is nothing but 2 pi by lambda. So D minimum is measured by calculating the first minimum voltage using the load, and D minimum is replaced by the load by shorting the circuit, or you can say by creating an equivalent load reference plane by using a short circuited load reference plane. So this shifts the by this shifting we can measure the minimum voltage. If the minimum is shifted to the left, the impedance is inductive. So how will you measure? How will you know the measured impedance is reactive or capacitive in nature, or inductive or capacitive? Reactive or impedance, the impedance measured impedance is inductive or capacitive in nature. So we can comment by seeing the minimum value which is shifted to the left or shifted to the right. If the minimum value is shifted to the left, then the impedance is inductive, and if it is shifted to the right, then it is capacitive. The phase of rho is calculated from this equation. Rho is equal to ZL minus Z0, ZL minus Z0 upon ZL plus Z0. So from rho and Z0, ZL can be calculated. So this is the way how can you calculate the beta. Beta can be calculated by using the simple formula. Beta is equal to 2 pi by lambda, and lambda g is nothing but 2 into distance between the two successive minima. Now measurement by reflectometer. So this is the setup for the measurement of reflectometer. Measurement by reflectometer. So reflectometer is nothing but a reflectometer gives the ratio of under root of ratio of reflected power to the incident power. So this is the setup for measurement of the impedance using the reflectometric technique. So here two directional couplers are used to sample the incident power Pi and reflected power P1 PR from the load, and both the directional couplers are identical except for their direction. The magnitude of the reflection coefficient is directly obtained on the reflectometer, and the impedance can be calculated from that. So from the reflectometer reading, we can obtain the value of rho, that is equal to under root PR by Pi. Reflection coefficient rho, VSWR and impedance can be calculated as per the formula available. The reflectometer indicates only the magnitude of the impedance but not the phase angle. There will not be any interference between forward and reverse for forward and reverse waves by property of the directional couplers. So the reflectometer accuracy is greatest at low VSWR values. That is, low reflection coefficient will give the higher accuracy, or low VSWR will give the higher accuracy in case of measurement of impedance by the reflectometer. Measurement of insertion loss. Next topic is the measurement of insertion loss and the attenuation. The microwave components and devices always provide some degree of attenuation. The output signal is always less than the input signal. So what is the reason? The signal has been attenuated within the system. The insertion loss of any device is defined as the difference in the power level arriving at the terminal load with and without the device in the circuit. So to calculate the insertion loss, the power attenuated is measured using RF substitution method and the power reflected using the reflectometer technique and added. So insertion loss is nothing but the reflection loss plus attenuation loss. Reflection loss is nothing but difference of incident power and reflected power to the incident power. And how can we measure this attenuation? Attenuation can be measured. Attenuation can be measured using this formula. So first of all, I will measure this P naught upon Pi. So for calculating this P naught upon Pi is nothing but insertion. If I measure this Pi upon Pi minus PR upon Pi is nothing but the reflection loss. Attenuation loss is nothing but the P naught upon Pi minus PR, and insertion loss is nothing but P naught upon Pi. So by taking this log, we can get the insertion loss, that is 10 log P naught upon Pi. This value will be in dB, and the reflection loss is nothing but 10 log 1 minus PR upon Pi, and attenuation loss is nothing but 10 log P naught upon Pi minus PR. So how can you represent this attenuation loss, reflection loss, return loss in terms of VSWR or in terms of reflection coefficient? So reflection loss is nothing but 10 log 1 minus PR upon Pi. This is nothing but 10 log 1 minus rho or gamma square. So in this way we can represent this reflection loss, attenuation loss and return loss in terms of reflection coefficient as well as in terms of incident power, reflected power and output power. Now, measurement of insertion loss and attenuation by using the power ratio method. So in this method, the input power and output power are measured with and without the device whose attenuation is measured. Whose attenuation you want to measure. So this is the setup. In this setup you can see basically these are basically in this setup we are using micro source, pad, frequency meter, slotted line, crystal detector, the thermistor, power meter, which will give the value of power meter will give the value of P1. That is the power available at the port 1 at the input side, and in setup 2 you can see that the setup is same, only difference is that the device has been added in between frequency meter and slotted line whose attenuation has to be measured. So in this method the powers are measured by both the setups. The powers are measured, that is P1 and P2 are measured by using these two setups. After that we can calculate the ratio of powers which will be expressed in the decibel and which will be the value of attenuation. Due to the nonlinear characteristic of the square law, crystal detector, the powers measured and the attenuation calculated will not be accurate. Next is the RF substitution method. In this RF substitution method, the frequency meter is basically in setup 1 and setup 2. we can see that the network whose attenuation is to be measured has been added in between the frequency meter and slotted line. And in setup 2, we are using the variable precision attenuator. So in this, the only difference is that we are using the network whose attenuation is to be used in setup 1 and the variable precision attenuator in setup 2. So in this method, attenuation is measured at a single power position and therefore overcomes the drawback of power ratio method. So the power is measured using the setup 1 shown in this figure and whose attenuation is to be measured. So let the value of P watts. Now the setup is figure B is used to measure the power. In this setup, the network is replaced by the precision calibrated attenuator, and in this attenuator is adjusted to obtain the same power level P as in setup 1. So now the attenuation read on the precision attenuator, which would give attenuation of the network directly. So by using this setup 2, we can measure the attenuation loss and we can overcome the drawback of this power ratio method. Next is the measurement of phase shift. So for determining the phase shift, we are using the network electric length, so which is not possible to distinguish between 1/4 wavelength and 5/4 wavelength, because each wavelength corresponds to the phase shift of 2 pi radians. So here you can see that network phase shift is used, and the calibrated calibrated precision phase shifter is used. So by knowing the approximated length of the electric length of the network, the phase shift introduced by the microwave network can be measured using the setup. So the microwave source is modulated by 1 kHz sine wave, and H-plane T junction is used. H-plane T junction used for splitting the output of the source into 2 equal parts. And one is passing through the network whose phase shift has to be measured, and the other one through the precision calibrated phase shifter. The standard phase shift is shifter is now adjusted until the two demodulated 1 kHz sine waves on the CRO are in phase. So we have to modulate, or we have to adjust the phase shifter, standard phase shifter, until we are not getting the two demodulated sine wave of 1 kHz. So we can see the relative phase shift between the two networks are equal, and the readings of the precision phase shifter will give the phase shift of the network. So this is the measurement of phase shift. So, and this is the measurement of dielectric constant. So basically this the electromagnetic property of a non-magnetic material or a medium can be completely specified by its permeability, conductivity, and the dielectric constant. So permeability mu is related to the magnetic force, and the conductivity sigma is related to the electric charge. The dielectric constant epsilon is the measure of the efficiency of transfer of electric charge, and the dielectric constant is also referred to as the permittivity of the medium. It can be represented as multiplication of epsilon naught and epsilon r, where epsilon r is the permittivity of the relative permittivity, and and epsilon r can be represented as epsilon dash minus j epsilon double dash, where epsilon r is equal to epsilon dash 1 minus j tan delta, and tan delta is known as loss tangent. So we can measure the dielectric constant by using two methods, that is waveguide method and cavity perturbation method, so which will be discussed in the next lecture. This is all about the measurement of the VSWR, attenuation, insertion loss, and impedance.